welcome back. In this video, we're going to work through an example where we analyze the motion of a particle along a horizontal line. And we end up drawing a diagram showing the motion of the particle. So we'll do it step by step. So here's the position function. It says a particle moves along a straight line with position function given by s of t equals 2t cubed minus 21t squared plus 60t plus 12, where t is greater than or equal to 0, and it's in seconds, and s, the position, is in meters. So part A says find functions for its velocity and acceleration at time t. So recall that the velocity of a particle in motion is just the first derivative of the position function. So the velocity as a function of time is the first derivative, s prime of t, which in this case is 6t squared minus 42t plus 60. That's the velocity at time t. So the acceleration, remember, is the rate of change of the velocity. So that's going to be the first derivative of the velocity function, or the second derivative of the position function. So acceleration at time t is the first derivative of v of t, so it's 12t minus 42. All right, so now the question is, when is this particle at rest? So the particle is at rest when its velocity is 0. So we're just going to take that velocity function and we're going to set it equal to 0 and solve that for t. So I see here I can divide both sides by 6 to make my polynomial a little bit simpler. So I get t squared minus 7t plus 10 is equal to 0. And that factors, so I'll factor it as t minus 2 times t minus 5. So now we can see that this is 0 when t minus 2 is 0, or when t minus 5 is 0, which means t equals 2 or t equals 5. So the particle is at rest at 2 seconds and at 5 seconds. So 2 seconds after it starts moving and 5 seconds after it starts moving. All right, let's move on. So part C says, when is the particle moving forward and when is it moving backward? So the particle is moving forward when the velocity is positive, because it's the velocity, the sign of the velocity tells us what direction it's moving. So when the velocity is greater than 0, it's moving in the positive direction. When the velocity is less than 0, it's moving in the negative direction, or backwards. So let's take that velocity function and see when it changes sign. Well, we know when it's equal to 0, so it can only change sign when it's 0. It may or may not change sign there, but those are the only places where it could change sign. So we make a sign diagram to check both sides of both of those places where it is equal to 0. So here's the timeline. There's time equals 0, and then I put 2 and 5 there because I know the velocity is 0 at 2 and at 5. And at time t equals 0, the velocity is positive 60. So we know it's moving forward when time first begins. When t equals 0, the velocity is positive 60. So we know it's moving forward then. But now we have to check all these other times. Since the velocity is a continuous function, we know it can't change sign in between the places where it's 0. So between 2 and 5, it's either always positive or it's always negative. And between 0 and 2, it's either always positive or always negative. So all we have to do is choose one test value for t in each of these little subintervals. So between 0 and 2, I'm just going to choose t equals 1 as my test point. So I have to calculate v of 1. If I plug in 1 into the velocity function, I get 6 times 1 minus 2 times 1 minus 5, which is 6 times negative 1 times negative 4, which is positive 24. So the velocity is positive at time t equals 1. Well, that means it's going to be positive on that whole interval between t equals 0 and t equals 2, because it's a continuous function. It can't cross the t-axis again, right? So we know it's always positive in that interval. So I'm going to put a little plus sign there. All right, so now in the other interval between 2 and 5, I just have to pick one test point, so I'm going to plug in 3. When I plug in 3 for t in the velocity, I get 6 times 3 minus 2 times 3 minus 5, which is 6 times 1 times negative 2, which is negative 12. So the velocity is negative at t equals 3, so it has to be negative on the whole interval between 2 and 5. So I'm putting a minus sign there. All right, so when t is greater than 5, I'm going to just pick a number greater than 5. Let me plug in positive 6, figure out the sign of the velocity function at that number, and I know it's going to remain whatever that sign is all the way to infinity. So when I plug in t equals 6, I get 6 times 6 minus 2 times 6 minus 5, so I get positive 24 again. So now that means the velocity is positive when when t is greater than 5. All right, so now we can see that the particle has to be moving forward on the interval from 0 to 2, and we're including t equals 0, but we're not including t equals 2 in that interval, because we can see from our timeline that when t is equal to 0, the velocity is positive. But when t is equal to 2, the velocity is 0. So the velocity is only positive from t when t is greater than or equal to 0 and less than 2. And it's also moving forward on the interval from 5 to infinity. So when t is strictly greater than 5, the velocity is positive, so it's moving forward there too. All right, when's it moving backward? Well, it's just moving backward on the interval between 2 and 5, not including the 2 endpoints, because when t is equal to 2 or t is equal to 5, we know the velocity is 0 there. So now let's draw a diagram showing the motion of the particle along the horizontal line. So it's traveling back and forth along a horizontal line. And what we're going to do is we're going to plot the positions at the times when it stops and the times when it turns around. So we're going to plug in times. So the first time we're going to plug in is 0, the starting position. Then we're going to plug in the first place where it stops, and then we're going to plug in the second place where it stops. And then we're going to also figure out in between those places which direction did we figure out it was going, because we're going to have to indicate that in our diagram. We're going to show the direction of motion in between those points. So when we plug in t equals 0 into the position function, we just get s of 0 is positive 12 meters. So that means it starts out 12 meters to the right of the origin, okay, where the distance is 0. So it starts just a little bit to the right of the origin. We know it's moving right between 0 and 2, and so when we plug 2 in, it should be something to the right of 12 meters, right? So we get 2 times 2 cubed minus 21, 2 squared, plus 60 times 2, plus 12. And when we add those up, we get 64 meters, which makes sense because we've moved from 12 meters a little bit further to the right to get to 64 meters. Then we know it turns around at that point. It goes left for a while. So let's see how far it goes to the left. We plug in t equals 5, and we get 2 times 5 to the third minus 21, 5 squared, plus 60 times 5, plus 12, and that adds up to 37 meters. So it's moved a little bit to the left. It's gone from 64 meters back to 37 meters. And those are the only places where it stops. So now we know that after t equals 5, it starts moving right again, and it just goes on forever to the right. So now let's draw the motion. The diagram is going to show the places where it stops, the places where it turns around, and also it's going to indicate the direction of motion in between all those points. So here's the horizontal line on which the particle is traveling. So this is not the timeline, this is the position line, s of t. So here's the origin. When t equals 0, it starts out 12 meters to the right of the origin. So there's where it's starting out. Then it moves to the right for 2 seconds, and when t equals 2, it stops momentarily at 64 meters. Then at that point it starts moving to the left again for 3 more seconds. So when t is equal to 5, where is it located? It's located at 37 meters. And then at that point it turns right again, and then it just moves right forever after that. So this is the motion of the particle. We can see where it starts, we can see the direction it's moving for the first 2 seconds, and then for the next 3 seconds, and then for the rest of time after that. We can see which direction it's going. All right, let's keep going. So part E says, find the displacement of the particle in the first 5 seconds. So displacement means the net change in position from t equals 0 to t equals 5. Okay, so it's not the same as distance traveled. It just means what's the difference in its position at t equals 5 from t equals 0. So all we have to do, so here's the diagram that we drew before. So notice from t equals 0 to t equals 5, it goes from 12 meters to 37 meters. That's the displacement. That's the change in position. So it's s of 5 minus s of 0, or 37 minus 12. 25 meters to the right of where it started. That's it. That's the displacement. So what about the total distance traveled in those first 5 seconds? That's a little different. The total distance traveled in that first 5 seconds is the distance traveled from t equals 0 to t equals 2, and then the distance traveled from t equals 2 to t equals 5. And just from looking at it, we can tell that's going to be more than 25 meters. So how do we find it? Well, we just have to get the distance from for the first 2 seconds, so that's absolute value of s of 2 minus s of 0, plus distance traveled in the next 3 seconds, from s of 2 to s of 5, but we have to take the absolute value, because remember, distance is always positive, so we're taking the absolute value. We don't want any negative distance. So we get the absolute value of 64 minus 12 plus the absolute value of 37 minus 64. So we get absolute value of 52 plus absolute value of 27, which is 79 meters, which makes a lot of sense. So the distance traveled was greater than the displacement. Distance traveled is always greater than or equal to displacement. Displacement, by the way, could be negative. If the particle ends up to the left of where it started, then the displacement would be negative. But distance traveled is always, always positive. All right, let's keep moving. So in part G, it says, when is the particle slowing down and when is it speeding up? So we do have to find the acceleration function. Well, we already found the acceleration function. The acceleration a of t was 12t minus 42. We need to first figure out when is the acceleration positive and when is it negative. So the sign of the acceleration tells us which direction the acceleration is pushing the particle. If the acceleration is negative, then it's being pushed, the particle is being pushed in the negative direction. It might be moving in the positive direction, but it's being pushed in the negative direction, the opposite direction. If the acceleration is positive, it's being pushed in the positive direction. So let's find out where the acceleration is positive and where it's negative. So we first set it equal to 0 to see where it might change sign. And we get, it changes sign potentially at t equals 3.5 seconds, 7/2 seconds. So let's write our timeline again, and let's mark off 3.5 seconds. Now when t is between 0 and 3.5, so when t is less than 3.5, we can take any number, say 1, any number in that interval, like 1, plug it into the acceleration function. So 12 times 1 minus 42 gives us a negative number. So that means acceleration is negative on that entire interval. Okay. And then the interval between, or after 3.5 seconds, so when t is greater than 3.5, we just plug in any number like 4. 12 times 4 is 48, minus 42, that's a positive number. So acceleration is positive forever after that. So where is it slowing down? Where is it speeding up? Well, to figure out where it's slowing down, we need to figure out what direction it's moving. Well, we already found the direction, so let's copy down our sign diagram for the velocity. We already got that sign diagram earlier. We know the velocity is positive between 0 seconds and 2 seconds, and the velocity is negative between 2 and 5 seconds, and then it's positive after 5 seconds. Where is the particle slowing down, and where is it speeding up? We have to look at where the acceleration is pushing against the direction. Where is the acceleration going in the opposite direction of the motion of the particle? So we have to look at where the sign of the acceleration is the opposite from the sign of the velocity. So for example, this interval between 0 and 2, we can see the particle is moving to the right. It's moving in the positive direction because velocity is positive there, but the acceleration is negative there. So something is pushing it in the opposite direction of its motion. That means it's actually slowing down on that interval. So it's slowing down on the interval from t equals 0 to t equals 2. But it's also slowing down here between 3.5 seconds and 5 seconds. On that interval, it's moving in the negative direction. The particle is moving backward because the velocity is negative, but its acceleration is pushing it in the positive direction. It's pushing it to the right because the acceleration, the sign of the acceleration is positive. So it's moving in the negative direction, but acceleration is pushing it in the opposite direction. So it's also slowing down from 3.5 seconds to 5 seconds. Where is it speeding up? Well, it's speeding up on the intervals where the acceleration is pushing it in the same direction that it's already moving. So imagine you're driving in your car, you're going forward, and you hit the gas. You're pushing the car forward. Or imagine you're falling to the ground, right? So if an object is falling to the ground, its height from the surface of the earth is decreasing, so its velocity is negative because it's approaching the earth, but the acceleration is also negative because gravity is pulling it to the earth. So as it's falling to the earth, it's actually speeding up because the acceleration is negative and the velocity is negative. So when the acceleration and the velocity have the same sign, it's speeding up. And so we can see this particle is moving in the negative direction and has negative velocity between 2 seconds and 3.5 seconds. And also it has positive velocity and positive acceleration from 5 seconds onward. So on the interval from 5 to infinity. All right, so it's important to remember that slowing down does not necessarily mean acceleration is negative. it means the sign of the acceleration is the opposite from the sign of the velocity. It's speeding up means that acceleration and velocity have the same sign. So they could both be negative or they could both be positive when it's speeding up. All right, that's enough of this example, and I'll see you in some other videos.